The ink is wet on this presentation, but we haven't done very much communicating about our next rover going to Mars, because we've been furiously, designing and building the thing, but NASA has really only recently started announcing that this rover exists, and we now have a launch vehicle, so that's always good. We have a way to get to Mars. So I'm really just sort of getting into the swing of communicating about our next rover going to Mars. Now, I work for the Mars Exploration Program, which is based at NASA headquarters in Washington and at JPL. So my job is to really communicate about all Mars and all of our Mars missions. And so I know, a little bit about every orbiter, every lander, every rover that's been flying around the red planet. And, we have many more plans for the future, including, as Bill mentioned, NASA does have plans to put humans on Mars in the 2030s. Now, there are plenty of other people who claim that they're doing that earlier, and, more power to them. But NASA's plans are to bring humans to Mars and to bring them back safely, and to do it in a very methodical manner. And we are sort of plodding toward that goal. I don't know, Clyde, if you wanted to play, Claude, if you wanted to play the that 50 years of exploring Mars video. I had a video to give you kind of the context for everything.
Okay, if you'll give us a moment to switch the video over, the audio.
It's just a formal video. It kind of gives you the idea of like, wow, we've been exploring Mars actually for 50 years.
Okay, I think I have you on some small speakers now, and John is bringing up that video now.
Good. I'm going to keep my mouth shut.
Okay, small speakers don't sound bad, actually.
Yeah.
This should be right. Hey, there she goes. That's data.
Cursor off the screen.
made on Earth. The successful landing of Curiosity will stand as an American point of pride far into the future.
I just want to call and say congratulations to the entire Mars Science Laboratory team and really all of JPL. You guys should be remarkably proud.
Okay, stand by while we switch the audio back. Okay, you're back on the large speaker system again, and John's bringing up your PowerPoint again. Okay, it's up.
Lovely. So, the idea of that is just to give you a sense that NASA truly has been exploring Mars for 50 years. So we've been flying by the planet, we've been orbiting the planet, been landing on the planet, and now roving on the planet. And hopefully, in the future, we'll be sending astronauts to the planet. Let's give you a context of how long we've been exploring around that planet. And what's amazing is how much more work there is to do and how much we feel like we still don't know what's going on Mars. So if we go to the first slide, I guess slide number 2, excuse me. So we talk about, I'm following along on my PowerPoint, and I'll just ask whoever's driving to advance the slides. So Mars Exploration Program, we have kind of a thematic program, and we have 4 science goals that guide our efforts. Now, I said before we've been exploring Mars for 50 years. These science goals are probably only about 20 years old, but we realized that we really need to be very thoughtful and methodical about how we try and answer the biggest question we want to know about Mars, which is, did life ever arise? And that is NASA's huge question for throughout our solar system and beyond our solar system. Are we alone? And it's such a fundamental human question, and it's really guiding our efforts right now. So even with our closest neighbor, which we have been interacting with for 50 years, we still can't answer that question. So hopefully this Mars 2020 rover, which I will be speaking about tonight, will help us answer that question, because we've been spending a lot of time out over at this other planet. We still don't know if Mars ever had life. So the Mars Exploration Program, whether it's landers, rovers, or orbiters, has these 4 goals. Again, searching for life or previous life, and figuring out the climate, the geology, how those things interact. Did they give rise to life? And then preparing for our astronauts. So these 4 things are guiding everything that we're doing. And I'll keep referring back to these kind of 4 goals when we are talking about this future rover and some of our past missions as well. Is everything going okay, Claude? I see your...
I was just making sure I knew how to make you full screen. I had a little banner on the side. No, we're doing fine.
Stop it! Sorry, cat. There's a cat scratching the couch. That's how I stop them from scratching the couch, just scream at him. He's a cat, but he sort of, they just walk through here. So if we go to the next slide, that would be slide 30. So we have a strategy for achieving these 4 science goals, which is, was there life? What's the climate? What's the geology? Prepare for humans. So our strategies have been evolving as we are getting a little bit better at these missions. Now this slide shows this graphic with all sorts of missions and their years of launch represented. And the red missions are missions that have flown, that have already gone. And these orange missions, these little orange boxes, are the missions that are in development or will soon fly. Now, those blue bars at the bottom are kind of our strategy. So for earlier missions, we didn't even know if Mars had liquid water, had frozen water, had ever had water. And key to figuring out if life is extant anywhere is there liquid water? Was there liquid water? So for a while, our strategy, starting with the Pathfinder program, which was 20 years ago, this coming summer, so 2017, will be the 20th anniversary of the landing of Pathfinder. Sorry, I had to throw the remote at the cat. And we first were trying to figure out, does Mars have water now? Did it have water ever? And the strategies below, follow the water, are explore habitability and seek signs of life. We have moved into this new strategy with the current mission on Mars, Curiosity, and this future mission is we are figuring out, did Mars have conditions for life? So before looking for life on the surface, looking for creatures, we have to figure out, does Mars have conditions suitable for life? Could anything live there? And so with the Curiosity rover and this next rover, we are exploring conditions of habitability. Could it have been a place where life could develop? And let's look for life. Now, Curiosity, and I apologize, I'm going to refer to this previous rover or current rover quite a bit, so I apologize if I'm doing insider baseball. We call it the curse of knowledge, where we forget, that we're in this bubble. So the Curiosity rover, and I will talk about the Curiosity rover, was sort of in this next blue zone of habitability and seeking signs of life. Notice the NASA language is very careful here. We don't search for life. We're not searching for things creeping around. We're seeking signs of it, which could be, extinct life, basically, that left its mark in the fossil or rock record, or it could be current life. No one at NASA thinks that there is probably life on Mars now, and we really hope to be wrong. We just don't have any proof that there's ever been life or that there is life now. But we are seeking signs of it. Can we make inferences? We don't know. Let's go to the next slide. Oh, look at this beautiful Mars fleet. So this is slightly inaccurate because we had to postpone a mission last year. But you can see in the sky a fleet of orbiters, and you can see on the ground rovers and landers that have landed on and explored Mars. Now, the little tiny inaccuracy is that we have a lander there represented in 2016, InSight lander, which was going to explore the interior of Mars and figure out if Mars is still an active planet. And that had to be postponed. So that lander will launch in 2018. Here we have it listed as 2016. And then we have ExoMars rover, we have these future rovers, and the 2020 rover. So all of these, in some way, have been either following the water, that exploration kind of strategy, or understanding habitability, or seeking signs of life. So all these things, we're trying to be very thoughtful about the spacecraft we put above and on Mars to always be kind of following in these strategies. This really came about when the Viking lander landed, and some of you probably remember that. That was 40 years ago, this summer, July 2016. And there was a lot of conflicting information and confusion about some of the life science experiments on Viking. And there were two people that, one person said, no, this searching for life experiment on Viking says, life never developed there. And someone else said, yes, it says definitively that life developed on Viking. And with this confusion, we realized that experiments probably had to be developed in a different way, and that perhaps we had to approach the question of, is there life on Mars, a little more, like back up a little bit and say, okay, let's just get to the fundamental, like could Mars have supported life? Well, let's look for that in the fossil record. And then start thinking about looking for signs of life, and then extant life. So, sorry, too much information. Let's go to the next slide. So in some of these exploration strategies, one of those was habitability. Could Mars have supported creatures? And we have determined that with the Curiosity rover, yes. The place where Curiosity is working now, and Curiosity just passed her 4 Earth year anniversary on Mars. I'm listing here the top 6 science discoveries. Don't worry, the next slide will have the other 3. Curiosity answered that question of habitability. This place in Gale Crater was once a standing freshwater lake and had sufficient oxygen, had sufficient sunlight, and had sufficient chemical compounds, sort of raw ingredients, that microbes, or very, very primitive microbes, could have lived in Gale Crater. So this number 1 here of the top 6 science discoveries, it was top 5 for a while, and then we had to amend this to make it top 6, which is good. Another discovery. Gale Crater, and hence other places on Mars. You can't quite extrapolate the whole planet, but this place could have supported life. We found organic carbon in the rocks, and that could be a sign of life. However, we couldn't rule out that organic carbon wasn't put there by a chemical process. We could not say that organic carbon was a biosignature or a signature of microbial life that left its sign in the rock. We can't figure that out with Curiosity's instruments. And we have detected methane spikes in Mars' atmosphere. There's a lot of controversy about methane in Mars' atmosphere based on some ground-based data from Earth. Some ground-based telescopes on Earth had seen spikes of methane in the Mars atmosphere. Curiosity has seen those spikes as well, and we have no idea what's causing them. We cannot say that they are caused by living things metabolizing. We cannot say that they are chemical weathering in rocks either. We don't know. And what's so interesting is that they seem to be seasonal. They happened for a month. Crazy spikes of methane. And then they stopped, and they have not been repeated. So it's a very interesting conundrum on the methane thing. So Curiosity has seen evidence of habitability. Mars could have supported life, but it can't answer definitively, are these things created by Martian life or previous Martian life? Frustrating. Let's go to the next slide. Okay, a few other things that satisfy some of those 4 Mars exploration goals that Curiosity has done. Assessing radiation. Now, radiation has a big connection to whether we think that Mars could support life currently, because there's terrible, terrible toxic radiation that comes down to the surface. Mars does not have a global magnetic field that protects, say, on planet Earth, we are protected by this global magnetic field from the sun's radiation or cosmic radiation or things coming from big outbursts off there in the cosmos. Mars does not have that. So lots of radiation is reaching the ground on Mars. So the Curiosity rover was helping prepare future human explorers by measuring radiation, both actually on the journey to Mars in its spacecraft and as it's on the surface. So Curiosity has given a lot of good information to the people who designed astronaut suits, for example, about the amount of radiation reaching the surface. We did figure out that, at least in Gale Crater, where Curiosity has been exploring for 4 years, there are signs in the rocks, in the organic compounds in the rocks, that there was standing fresh water and that there was a thicker Martian atmosphere to be able to support liquid water at the surface. And Curiosity did find that it was it drove over a stream bed. So it's in a crater, and streams were coming down from the edge of the crater and filling that crater with water, eventually a lake, And Curiosity found, that there was definitely persistent flowing water. Now, throughout Mars, you can't say that there's persistent water for millions of years, but we think there was persistent flowing water perhaps for tens of thousands of years. All of this helps answer the question, if there was persistent water, could microbial life 3.5 billion years ago have developed? And we still haven't been able to answer that. And it's amazing that Mars was so Earth-like at one point, and it's so frustrating that we can't answer the question. And if it was Earth-like at the same time that planet Earth was developing microbial life 3.5, 3.8 billion years ago, we still can't answer whether was Earth unique in that all sorts of things combined together and then suddenly we have humans. And we don't know if that ever happened on Mars. So let's talk about the next rover. So I diverted a little bit in talking about Curiosity, but wanted to show you that Curiosity and its goals fit into these overarching goals of, is there life? Tell us about the climate, tell us about the geology, and how can you help us prepare to bring astronauts to Mars and bring them home safely? So let's talk about this next rover, which has a very sexy name, Mars 2020. And that's because it hasn't been named yet. So it falls on my team, and I'm a small cog in a large machine, to develop a naming contest to name this next rover. So at some point next year, it'll have a far more interesting name than its launch date than Mars 2020 rover. But for now, we just say Mars 2020. So I apologize, I can't call it anything other than that. We typically have naming contests in which people, usually children, write essays to, they pitch their name, they have to write us an essay. All 4 of the rovers that have gone to Mars have been named by girls. So they seem to be writing the stronger essays. So I do challenge the little boys I encounter in my outreach activities to, come on, be the first boy to name a rover. It's, can't have the girls be 5 for 5. Anyways, that'll happen next year and we'll have a better name. So let's go to the next slide. So this one, we're going to that in our evolving strategies. We're not seeking the water anymore. We know Mars had water, it has current frozen water. Now we're firmly in the exploration strategy of seeking habitability, such a hard word to say, and signs of life. And we're very careful to say, not seeking life, seeking signs of life, because that gives us a nice open bucket to look for previous life. So this 2020 rover going to figure out where it lands. Was that place habitable? Did it have those raw materials needed for perhaps microbial life to develop? And we're seeking biosignatures. Did that life change the rock? And did it leave a mark of its existence? Because we believe that Martian life, if it developed, would have gone extinct, if it did, millions and millions of years ago. So everything we do is very much about geology and geochemistry. So it's really, microbes do leave traces on rocks. And so we are looking for rocks that can preserve those traces and, preserve them over time. And would they be deep underground? Possibly, because of all the weathering that happens to rocks at the surface. Now, one exciting thing about this rover is that we are going to cache samples. So this rover can take rock cores, and it will have a pile of rock cores sitting on the surface. And then some future mission, as yet unnamed and as yet unpaid for, will come and bring the samples back. Now, we feel like there's a lot more we can learn by taking these rock cores, and they're a little thicker than a pencil. That we could do analyses in Earth laboratories with big giant machines, larger spectrometers and things to analyze these rock cores on Earth. We feel like there's a lot of questions we probably can't answer with the technology we can bring on board a rover. The Curiosity rover had 2 analytical instruments inside it. but they can only do so much because they have to be the size of a bread box or something. So we want to save these rock cores for eventual return to Earth. And any mission that goes to Mars now, it has a to-do list, prepare, do something to prepare for human exploration. Because again, we want to make sure we can get the astronauts there in safety, so protect them from radiation. Curiosity helped do that. And then how are we going to be making raw materials on planet Mars? I mean, we're going to have to, we can't bring stuff with us. So if you all saw the movie The Martian, I mean, part of that was very accurate in terms of sending a spacecraft to Mars, having it land, and then it sits there quietly and makes its own fuel for its return trip to Earth over years. So something like that is actually quite accurate, that we need to make everything that make some of the things that the astronauts do in situ. So this next rover, Mr. 2020, is going to have an experiment that's going to help figure out if we can make oxygen from the carbon dioxide in the Martian atmosphere. Let's go to the next slide. There she is. What a cad. So here's the latest computer design for this rover. I expect it to change about 17 times before it flies, because you might notice it's a little complicated. There's a lot of little things that happen, and there's many, many things that are still under development and design in this rover. So probably a lot will change. But if you are familiar with the Curiosity rover, the size and shape, design, spacecraft, landing method are very similar. So we were hoping that we could shave a little money off this mission by building on the shoulders of this previous rover. So, we've got the same mobility system, it'll use the same power system, has the same general configuration of a large rover with a mast and a head, and it's got an arm. So this rover is really building on the heritage of the previous rover, because we can't keep doing one-offs. Pretty soon we have to start, using some of the designs. We have made many improvements, or, I don't want to say that things were terrible at Curiosity, but, technology always steps forward. So there are many things about this rover that are a bit of a step forward. So there's the current design. Again, it'll change. If we go to the next slide. So here's what this rover is going to do. Now it will launch in 2020. I think it's September 2020, land in 2021. And it has a 1 Martian year or 2 Earth year primary mission. And then if it keeps lasting, then you just, it'll keep going. But it needs to achieve these things in its primary mission. It's got to find rocks, certain rocks that have the potential to preserve biosignatures. So it's really looking very specifically for rocks that we know have the potential to preserve any information that, if microbial life developed, it left a record in these rocks. And we know what kinds of rocks do that. And we know that those rocks are there from orbit. So we have 8 potential landing sites. All of them have the rocks and minerals identified to potentially preserve signs of life. So it'll go to one of those places. It'll find the rocks, drive around, look very carefully for the rocks, be very selective about rocks it drills into. I think it can take a maximum of 37 cores. It's going to try and get as many cores as it can into 2 Earth years. And then if the mission extends, I don't know if it has to get to 37 in that first Martian year, or if it gets as many as it can the first Martian year, and then anything else is gravy. Because this rover doesn't have the ability to return those samples. So we have to just keep collecting them but I believe that the sample container can hold 37. Why 37? I do not know. I do know that it looks like a big ball, and it opens, and there's a flat surface, and all the cores pop in there. And number 4 on this rover, we're going to see about producing a useful thing, oxygen, both for breathing and for making fuel, inside the rover. So as an experiment, just a sort of demonstration of making oxygen on the surface. Now on the next slide, whew, nice busy rover drawing here. I'm going to tell you a little bit about the 7 instruments, and this is like major high level, just a sentence about each of these 7 instruments. Now it looks like there's many more 7 things listed on this particular diagram. That's because the instruments are sort of split and they have pieces all over the rover. But one thing that's nice to note is that as in previous Mars missions and in future Mars missions, an international effort, we do not believe we can get to Mars with robots or humans as just the United States. So we definitely work with many international partners, and I know that pool of international partners will grow as other countries develop their capabilities. But we do have an instrument from Denmark, from France, and from Spain. And then several of the principal investigators on these instruments are actually at JPL or scattered about the United States. And there's a huge science team, but of course there's a principal investigator for each of these 7 instruments. And I'm going to just list the instruments for you, starting at the head, so the mast that comes up. We'll discuss 2 things that are in the mast, and then I think they go to the body of the rover and then the arm. So those 7 instruments. And all of these 7 instruments are geared towards those 4 little goals for the 2020 mission I told you about. So searching for the suitable rocks, searching for potential biosignatures, making oxygen on the surface, and taking the rock cores. So let's go to the next slide. I have that should say Mastcam Z. So have you ever seen any of the beautiful, beautiful pictures that come from the Curiosity rover that look like New Mexico? They're like beautiful desert vistas of Gale Crater. That is what's called on the Curiosity rover Mastcam. So this is Mastcam Z. And the exciting thing about this camera is it can zoom in and out. The current rover can't do that. So it's adjustable. One camera is adjustable. But it can take video. So we're very excited. It's actually going to be able to record video, which is a capability we've never had before. And this will it's a science camera. It will take the beautiful vistas and help decide where the rover will drive. It's not exactly an engineering camera, which is really the eyeballs of the rover. But this one will help identify potential science targets and those rocks that the rover will then drive to start searching for these potential biosignatures. And this is going to be able to take 3D images too. So not only video, zoomability, but 3D. So excited about that one. On the next slide, we have SuperCam. This is quite similar to something that has flown also as well. It has the same principal investigator. This one is a laser and a camera. So the nice handy thing about having a laser on your rover is that it can zap rocks, which creates a little puff of plasma, and then a spectrometer at the same time reads the plasma, can tell you what's in those rocks. So in general, can give you a general picture of what those rocks are made of. That helps you identify science targets without having to drive up to them. So that is a really handy tool to zap things from far away and help guide science decisions. Apparently the first few months of this next rover's life will be quite frantic because they are trying to get as much, core and cache as many samples as possible. So they're going to be using this instrument a lot to really help them make driving decisions. Like, should we go left or right, or where should we go? How can we identify the proper rocks? We only have, sort of 2 Earth years, and that goes really fast. So the SuperCam is a laser that will zap rocks, use a telescope. The ChemCam, which is an instrument that flew on the Curiosity rover, was able to take black and white pictures through its telescopic lens. This one can take color. So again, a slight improvement on SuperCam. So this one will be very handy to figure out the mineralogy of potential science targets and whether it's worth going over to drill into them. Let's go to the next slide. So those 2 instruments, SuperCam and Mastcam Z, were on the head. Now we're on the neck of the rover. This is more weather instruments. So the, I can't say it in Spanish, but the Center for Astrobiology with the Spanish Space Agency, they are really good at doing the sort of weather instruments. And there's a suite of weather instruments that take all sorts of, temperature, pressure, barometric pressure, wind speed. Those instruments are on current rover Curiosity. This is another set of instruments. This one is going to look very closely at dust. Mars has constant dust flowing. It's a very, very fine dust, and it's magnetic. And that really poses a risk for human astronauts. That dust could get into your breathing apparatus, it coats things, it sticks to things because it's a bit magnetic. So this, not only taking, sort of weather, pressure, temperature data, is going to be looking very carefully at the dust. And the Mars dust has a huge influence on weather patterns because suspended dust in the sky controls heating, cooling of the planet, blocking sunlight. So MEDA is going to do a lot with, again, preparing for human astronauts, looking at, temperature, pressure, weather, wind, and dust concentration in the air. So that's going to be a handy thing to have. Again, this is one of the ones preparing for human exploration. Let's go to the next slide. MOXIE. Now we're at the tummy of the rover. This is the instrument, and can I just say that the people that wrote these instruments, 7 PIs, went to great lengths to come up with good acronyms. And I will tell you, we went through many contortions to come up with these awesome acronyms. MOXIE being one of my favorites because I can remember it, and I can somewhat tolerate MOXIE, so that not very much, but they go through great lengths to come up with these awesome acronyms. So MOXIE is an acronym. I can't remember what it is, but it has to do with oxygen production. So it's going to suck carbon dioxide from the atmosphere and separate it into carbon and oxygen and demonstrate, could this happen? Does that by way of these electrolytic plates, and it's taking the, sort of atoms through these electrolyte plates. So this is actually a very power-hungry instrument. It's going to heat up these plates to something like 400 C and separate, oxygen out, and let us know, is this a way that could work for the human astronauts? Is this an instrument? Does this technology, us make, raw materials for either breathing or fuel on planet Mars? So that's MOXIE, and we just love that name, MOXIE. And the principal investigator of this instrument just went up to Maine and went to some MOXIE festival in Maine. And they were probably wondering, with this guy from California with a Mars rover, what's he doing here? But anyway, he said, well, my instrument's called MOXIE. Spreading the good word. Also in the tummy of the rover, who was that?
Quick question. The heat source for that, is that going to be electrical, or is that taking some kind of heat exchanger directly from the RTG, the radioisotope thermal generator?
Oh, good for you. It's a mouthful, isn't it? It'll be taking heat from the battery that is heated, but that is fed by that thermoelectric generator. So the rover will have several batteries, and they'll be running in parallel, and MOXIE will have its own power source. Okay. But it is battery.
So it is an electrical heater then, it's not just taking the direct heat from, okay.
No. And the RTG, thermoelectric generator, plumbs heat throughout the rover. And MOXIE is one of the more power-hungry things, so it kind of is going to have its own power source. And when that instrument doing the thing, like other things have to shut down. So these rovers, I have the website in this presentation. You can go look at the power draws of some of these instruments. Some of them are ridiculously small. MOXIE is one of the bigger ones. So it has to have its own sort of path to get its own power. Next one we have, these are the nice people from Denmark. Or is it Norway? Norway. RIMFAX. So this one is ground penetrating radar. So it's the first time we've had radar on a rover. And this is to look at the subsurface structures underneath the rover. And this can detect subsurface ice. Now, we know that there's subsurface ice on Mars because often when meteorites impact the surface, sometimes, I won't say often, but sometimes we can take orbital pictures of new meteorite impacts, and we often see exposed ice. But other than that, we don't really know how much subsurface ice there is. And also, could subsurface ice be a place where microbial life could be living currently? It's protected from all that radiation by a layer of dust. We kind of wonder about, could that be a habitat? Because we know on planet Earth, on the Antarctic ice cap, where you think, gosh, nothing can live except those big emperor penguins that do the March of the Penguins. There's all sorts of microbes that live in the ice, between the ice crystals, all over planet Earth. So we wonder, could this subsurface ice, have microbes in it, or could that be a resource for human exploration? So this is going to be ground radar that's come out of the rover and going to create a little map of, structures underneath the rover. That's something we haven't been able to see before. And in the next slide, now we're on the rover arm. The next two instruments are interested in really, really fine scale, microscopic, looking at the mineralogy. And they have, sort of magnifiers, I should say microscopes that can look at very, very, very fine-grained mineralogy on Mars. And we're interested in really fine scale and fine-grained mineralogy because we are looking for signs that microbes acted on these rocks. For example, if you've ever heard of satellites on Earth, those are some of the oldest rocks on Earth that show interaction with microbes. And there are stromatolites found all over planet Earth, but there's a sort of big, current microbial colonies in Australia, and the colonies of these microbes leave what's called a biofilm on the rock, and that's actually preserved rock record. And we're interested in the next two instruments on looking at this fine-grained mineralogy. Can we tell from these rocks, wherever we're looking on Mars, have microbes acted on them? Do they show any of the signs of interaction with living beings? So Pixel is an instrument that's actually coming out of JPL. It's going very, very fine-grained mineralogy with an X-ray. And by the way, this is our only female PI. It's the first female PI, I think, in Mars history, at least recent Mars history of JPL. So excited lady. Always good for my line of work and inspiring girls that we have a principal investigator, though she is Australian. So this instrument's going to be looking at fine-grained mineralogy as well as the next instrument, which should say Sherlock at the top. This one's also looking at fine-grained mineralogy with a Raman spectrometer. So the last one's X-ray spectrometer. This is called Raman. This one's called Sherlock. And boy, that's another good acronym. And then he's added some component to this, which he's calling Watson. Isn't that sweet? So we love acronyms here. So this is going to be using lasers again to get an idea of the mineralogy. Were any of these rocks interacting with water, and were they interacted with microbial communities? Can we figure that out? Are there organic compounds? And is there any sort of sign that organic beings interacted with these rocks? Now, most of these instruments that I've shown you will be sending data back to Earth. But again, they will help us choose those rocks that we make into those cores, the rock cores. So these instruments, will be sending back their own data, and they have their own, sort of set of information that they send back, but they help us choose those great places to core and then cache or make a file of these rock cores. Let's go to the next slide. So I'm repeating this slide. So again, we're going to use all these instruments, as well as all of these sort of engineering things of the rover, the cameras that help it drive, to find the rocks that were altered by water or maybe microbes. Find the kinds of rocks that we know can preserve biosignatures. There's a lot of clay minerals on Earth that have this layered structure, kind of like, if you've ever had a baklava, like phyllo dough. we compare the rocks like they have these layered structures, and organic minerals get stuck in these layered structures. So we want to find rocks like that, capable of preserving biosignatures. Then this rover will drill these cores and put them in these specially sealed, very sterile sample tubes. Leave them on the surface, unfortunately. We don't have a cool rocket to send them back, so they're going to be left on the surface. And then this rover in particular will be trying out this oxygen production device. Let's go to the next slide. Why are we doing all this? So all those instruments are really in service, both of their own data, but finding these proper rocks. And this little animation kind of shows, if it's working, it's not working on my computer, but this little diagram is showing that red X shows, okay, the rover landed there. It's going to an area of interest, which are the blue circles. So from orbit, we've got some ideas that wherever the landing site is, there are 8 candidate landing sites, that wherever one of these landing sites is, has a region of special interest. And we'll take samples and we'll put them in one spot, drive off, take more samples, bring them back to that spot. So eventually this rover, when it's done its work, it's not going to cover a lot of territory because it is going to leave 1 or 2 piles of these sample tubes. And again, I think there's 37 of them. And they're sealed properly, they'll be in a pile. And then some future robot, actually they're doing testing at JPL right now, actually is going to have this robotic arm. It's going to pick up the sample tubes and put them into this round cache. This flat surface with all these holes, puts them into the cache, seals it up. It's all sealed and sterile. And then it's put into something, Mars Ascent Vehicle, and shot back to orbit, where it's captured by something else, orbit in Mars for a while, and then blasts off to Earth. Very complicated. We don't really have plans for that next leg of the samples journey. This rover is really just collecting the samples and leaves them in what's called a depot cache. So it's in a pile. And let's go to the next slide. Now, a few other things about this rover. So I've talked to you about the science, and the 7 science instruments in service of, figuring out, are there biosignatures? Could Mars have ever developed life? But one thing that's, of course, challenging for someone like me in the public engagement world is everyone is going to say, well, isn't that just like the Curiosity rover? I see no difference. Well, it has all these different science instruments, so that is different. So there's differences there, but also we have stepped forward the technology. So we had a successful landing with Curiosity. Now we are taking what we learned and making it, incrementally better. And all of this is also in service of sending astronauts to Mars. So we really want very, very accurate, safe landing system so that when we're sending humans, they will have a safe ride and get to where they need to go. Let's go to the next slide, which is 22. So new landing technologies are landing in the same way as a previous rover in that we come into the Martian atmosphere in an aeroshell. We slow down with chute. Aeroshell opens, there'll be a descent stage which will lower this rover down to the surface. And with Curiosity, we were actually very, pretty precise and very, very well inside the margin of error of our landing ellipse. So we really got to where we wanted to go. However, these are engineers. They want to do better. One better. So they developed 2 new landing technologies that will make this rover even more accurate. And what's good about this is that it's giving the rover itself the ability to make these decisions. So it's more autonomous landing. Now, when the Curiosity rover landed, it was pre-programmed to just follow all these steps. And there were a few things that it could kind of, sort of change, but in general, it was a pre-programmed sequence of events. Now, these next 2 landing technologies that are improved, one is called terrain relative navigation, and another one is called range trigger, will help. The rover actually has the smarts to be making these decisions as it's, flying through at 1,000 miles an hour, but it's able to compute some of this stuff. So this next landing technique that people are very excited about is this range or terrain relative navigation. Now that is, the rover has been given a map from orbit of its landing area, and in its brain, I keep pointing to my head, but in the rover brain, it has this map. It knows what to expect, and when it pops off its heat shield, it actually has these cameras, and they start looking down, and it compares the maps, and it can make its own decisions. It can, okay, I understand where I am now because I'm looking at this map that's been loaded on board my computer, and it can decide that it is going to hit something, or that it's not, the area where it's heading towards is not safe. So it can actually make all these computations based on a map that it holds, and then it takes pictures, compares those two, and looks for a safe place. So it can fire off these little thrusters to steer itself farther along in its journey if it needs to. Of the 8 candidate landing sites, there's the juicy science ones and the super safe ones. There's always this middle ground of, now we can get to some juicier, more interesting rock stuff because we have more precision in landing. We don't think we're going to slam into a mountain. But there's still a lot of, sort of give and take about how safe the landing site is. Let's go to the next slide that has range trigger. So that terrain relative navigation is a camera system. Range trigger is a radar system. This helps actually a little further upstream, so I should have switched these 2 slides, I realized. Range triggers helps the rover decide when to fire its parachute. So it understands better with radar where it is relative to the ground. Now before Curiosity, barely knew anything. And by the way, that parachute is triggered when it's going about 1,000 miles an hour. So it comes into the atmosphere going 13,000. It slows down through sort of just ablative heating through the atmosphere. It just sort of goes down. The spacecraft is slowed down in the atmosphere. But by the time the parachute fires, to slow it down to about 200 miles an hour, still going, 1,000. But this range trigger is going to be a radar system that helps the rover know when to fire the parachute. It understands where it is in space, and is it heading towards where it needs to go, and it can fire the parachute sooner, or if it's far away from where it needs to go, and it can delay firing the parachute. Before, that was all automated. Now the rover is going to have the smarts to be able to take in data, understand where it is, and make that decision, fire the parachute now or half a second. So all of this is going to help when astronauts are landing on Mars. If you're landing astronaut on Mars, you're going to need tons and tons of materials. We want to be able to land it all in the same spot. So these precision landing technologies are helping future exploration, because we want to get everything landing in the same place so the poor astronauts don't have to rove on the surface of Mars looking for their stuff. And did I repeat that? Yeah, I repeated that slide. Sorry, ignore that. Terrain relative navigation. I have one more slide. Let's go to the next one. V25. These are just sort of an overview of 5 fun facts about this rover. We did redesign the wheels, if any of you are familiar with the Curiosity. We did take a lot more wheel damage than we expected. So all of that information was fed into the design of the next rover's wheels, made them thicker, made them the sort of save mass, realized that we didn't need, these particular patterns that ended up being real failure points of the wheels. So we got some new wheels. One thing that's going to be very exciting is when we're landing, so during this entry, descent, and landing portion that I was just talking about, we're going to have cameras that can see both looking down, so you can see our descent. They're going to look up, see the parachute deploy, and they're going to record. So we've never had microphones recording the sounds of these things deploying, and there's going to be microphones that can record the sound of the rover as it works on Mars. So we're kind of excited about hearing the sounds. We've tried to fly microphones several times before, and they either got descoped, which means deemed unnecessary, or there was a microphone for the Phoenix lander, which landed in 2008, which its software was conflicting with something else, so it got de-scoped. On this rover, we'll be, of course, collecting rock.
Uh-oh. Oops.
And
Okay, we lost
all
your
of this
audio
is
for a
on the
moment.
next slide.
Let me turn off our video. We're having a little bit of bandwidth issue, it sounds like. Okay, maybe go ahead and try now. Uh-oh.
Hello? Did I go?
Okay, I think you're back now. No? Uh-oh.
Turn on again. Any more light?
I think we hear you now. Oops.
Okay.
We've lost your video.
What happened? Oops.
Oh, you're back now.
You're back.
I'm back.
Okay.
Good. Am I on?
Yes, you are. We'll leave our video off for the time being.
Oh. Yeah, I mean, you don't need to say nay. That was my last slide, so if anyone has questions, I welcome questions about Mars, about current, previous missions, or about this upcoming mission.
Okay, do we have any questions?
Well, I have one. Question about the collecting the core samples. A couple questions about the core samples. One thing, how long are the core samples going to be?
Oh, how long? Let's see. I don't have an exact centimeter, but the sample tubes I've seen have been like this. Do you have my video?
Yeah.
Imagine about the size of the length of, almost the length of a pencil. Maybe like the length of a pen.
Okay.
So what would that be? Is that like 10 centimeters? About 10 centimeters?
20.
I'm thinking about the sample tubes I've seen, and they look to be about 10 centimeters.
How deep are you going for the cores?
Well, that's the question.
Yeah, so it would be about 10 centimeters. They'll take the surface, the rock, and they'll abrade the rock a little bit to try and get a clean surface, and then they'll drill into it. I think it's about 10 centimeters. And again, I keep holding hands up. Like that, because I've seen the tubes. About like that. So, they can't get into extreme, unless they go to a place that they should have ancient rock. For example, Gale Crater, was a big giant crater scooped into the surface of Mars billions of years ago. And that's the reason why that rover was sent there, because the rock record would accurately reflect perhaps 3.8 billion years ago or 3.5 billion years ago. So old rock is what we're after.
And the other question I have is, wouldn't it make more sense to have the core samples done on the same mission that's going to return them? So they aren't just sitting on the surface for some unknown length of time being irradiated.
Yep.
Wouldn't that make more
It
sense?
would. Absolutely. And this was a question of resources. So, the samples will be in tubes that will protect them from radiation. So they are in very carefully sealed and sterilized tubes. Mm-hmm. But no, it's very annoying to cache the samples and then have to wait a long time before they come back. So that's very annoying. And previous designs of this rover did have the rover would carry the sample cache with it and would have to pick up the samples and put them in the cache. And then would even have a little rocket on the back that was going to blast off and destroy the rover. And then because of resources and the ability to build all that and how much it would cost, that was all de-scoped. So that's a bummer. It feels crazy to leave these things on the surface.
Go ahead.
I have a question. When you are preparing to send a human mission, do they have a projected date that they are shooting for with humans, and how many humans are they planning to send?
Projected date is 2033, and that is being super duper optimistic. There's so much we have to finish and figure out before we send astronauts. But apparently there is a very favorable launch window in 2033. So that's the sort of year we're going for. I think a lot of things could change.
Did she say 2033?
2033,
Yes, that's what
yes.
she said.
I think I'll still be alive. It's got to happen before I turn 100.
And my belief is that, private industry or international partners could push that date closer. But right now, if NASA continues on its progress with its current funding, which of course never enough, right? 23 is the date. We haven't built the rocket to take people yet. And by the way, the rocket, the Orion capsule, which would go in the Space Launch System rocket, holds either 4 or 6 astronauts.
Nice.
They like female astronauts because we're small. We require less resources, so apparently half of the crew is definitely going to be.
The Raman spectrometer, I think Sherlock it was.
Sure.
Believe me, I'm no biologist, about as far from one as you can get. But I hear that one thing that would nail biology would be to be able to tell a preference for chirality, handedness in some of the organics. Will that Raman spectrometer be able to determine the chirality, the chirality of any organics that it sees?
That is an excellent question. I do not know. Have you heard Chris McKay speak? He's the one who's always talking. He's at NASA Ames, and he's a big astrobiologist, and he's often talking about the handedness and whether, will we be able to figure, will things formed off Earth have the same handedness? Or I believe it's like amino acids or something. Mm-hmm. So I do not, I'm not sure that would be preserved in the rock record. I'm not positive in terms of, so I would say, I really don't know. I mean, it's really looking for just signs of organics and whether it could get to anything more in-depth handedness in those organics, the amino acids and things. Fascinating.
Any other questions?
Ask me more.
Byron.
Well, what kind of rocks preserve microbial traces?
Well, one thing that the Curiosity rover was really looking for were these clay minerals. One particular class of those minerals was stalactites, and they're ones that have this layered structure. And apparently on Earth, all sorts of organic compounds get preserved in these layers. So there are rocks that have sometimes very loosely organized structures that organic compounds could be. They're also looking for rocks that form or altered in water. So they don't want anything that looks like it was acted on by volcanoes or things that were acted on by like methane processes, because that would destroy any sort of organic compounds. So it would be things that are associated with Earth, preferably freshwater, and more recent rocks altered by freshwater. Sometimes, they also can be volcanic, but some of the cherts apparently can, which have a high silica content, they can preserve organics as well.
Are there any possibilities that they could find stromatolites there?
They're doing a lot of stromatolite, that's a great question. They're doing a lot of stromatolite research around Earth to figure out, would they see those same traces, and they probably see them visually. They're like magnifiers, microscopes, because they've done cross sections of stromatolites here on Earth, and they're going to look for those kinds of traces on Earth. We don't have a way to section rocks on Mars, so we can't slice them. But they would look for stromatolites, and they would look for things that might have the same structures or maybe layered texture that some stromatolites have. So those are of great interest to us on Earth. We have a lot of them here at JPL that people study, and they're firing the spectrometers at them to get a baseline for like, oh, okay, we could look for that on Mars, if we see a similar signature. I keep talking about microbial life, and people wonder, like, well, aren't we looking for higher life forms. I mean, microbes, boring. The reason why we look for microbes is that we believe that Mars went through a really radical, whole global environmental change, and it started losing its oxygen at a certain point in its evolution. And free oxygen is what allows multicellular life forms to metabolize. We need more oxygen than Mars currently possesses. So we believe that Mars had a thicker atmosphere and more oxygen in its past, but we think that, by the time it started losing oxygen, life, if it did evolve, couldn't have evolved past single cells. So that's why we really sort of have our hopes pinned on microbes, because that's only as far as Mars probably could have gotten in its planetary life evolution. Again, if it evolved.
Sarah, what's the NASA budget for this thing?
This thing, great question. The last rover was 2.5 billion with B. I don't know. Of course we hope to save money because we didn't have to develop so many new technologies. So I have a feeling it's less than that, and it's got a much shorter time horizon. It's about 10 years in development. And that's a great question. I should know that because that is a question
I think I might vaguely recall hearing the number of 1.6, but that might be obsolete.
A lot.
Yeah.
I apologize.
Who knows? The MSL, the Curiosity was delayed a lot, and so that cost a lot more. So
it certainly did, and then also it was developing so many new technologies. So this one, we've incrementally improved the technologies, but there's a lot of development that didn't have to happen. So,
and the foreign governments are contributing the instruments pretty much themselves. That we aren't. The U.S. is not paying for those, right?
Correct. They are developed and built, but they do. I think the teams that develop them certainly do have to put in a little bit of money in terms of their time and in kind in terms of the development. But now it's all part of the overall NASA budget. That, when we get RIMFAX in, we have to pull it.
Okay, I think we better let Sarah go, so please join me in thanking her for an excellent speech. Thank you so much. And Sarah, we hope to see you again here in Big Bear fairly soon, and all we can say is thank you so very much for the talk, and you're welcome here anytime, and let me assure you, you are an honorary Big Bearian, so.
Welcome to visit. I have to see your solar observatory. I've never seen it.
Well, I think you have a couple of email contacts here, so let us know.